And today, I'm going to talk about using those hyperspherical coordinates for ultracold three-body recombination of fermionic atoms. And I should really point out that Hiroya Suno is my postdoc. He actually did all the hardcore calculations and all the tough stuff on this that I'm going to talk about. And this is in collaboration with Chris still. And everybody's at the meeting, so if I can't answer your questions, one of those guys surely can. And I put in the obligatory pretty picture from Colorado, but I had to offset it by a pretty picture from Kansas. See, we have pretty stuff there too. So three-body recombination, we've heard it mentioned a few times. So I'll just put up what we mean by it. And it's just three free atoms colliding, making a molecule, and the third atom carrying away the excess energy and momentum. You have to have that third particle there to conserve total energy and momentum. And of course, that free particle and molecule at the end are going to separate with the energy equal to basically the binding energy of that molecule. And that binding energy is huge on the scales of ultracold collisions. We heard some idea of what those energy scales were, nanokelvin, microkelvin. That works out also to be a pico EV for people who are more used to thinking of electron volts. Now for spin polarized identical fermions, so everything with their spins aligned, there's a few questions you might ask. Why isn't the recombination rate simply 0? For those of you in the ultracold community who've thought about this, you expect, in the ultracold limit, only S waves happen, right? Only S wave collisions are going to happen. And so identical fermions, which have to collide in P waves, there shouldn't simply be no recombination. That's a typical argument. I've heard it many times. We'll go over that. What happens near a Feshbach resonance? This you can ask for recombination of any atoms, bosons, fermions, bosons mixed with fermions, whatever. What happens near a Feshbach resonance? That's important to understand, and you probably already have an appreciation of this because we've heard in nearly every ultracold talk that they're using Feshbach resonances to manipulate these things. So to understand what happens to the three-body recombination, which, by the way, and I didn't say it explicitly, means that those atoms are lost from your sample. Okay? And does anything special happen when you're a degenerate Fermi gas? That's what a DFG is. Sorry, I made the abbreviation. Degenerate Fermi gas. That's when you take fermionic atoms and cool them down till they're all in their lowest states. And for fermions, there just has been no three-body recombination studies to date. Well, let me point that out. Let's go back to the first question. Why isn't the recombination rate 0? Well, we actually know the answer already, even experimentally. We know the Wigner threshold law says it's suppressed. The P-wave collisions between two fermions is suppressed, but it's not 0. It's simply small. And an experiment was done. Debbie Jin at Gilla and John did the theory for it. And you can see nice agreement, right? Here's the Wigner threshold law. This is two-body elastic scattering, two fermion isotopes of potassium, or not two fermion isotope. It's a fermion isotope with different hyperfine states. Gives you an S-wave collision, which is constant at threshold. And then in the same hyperfine state, they give you P-wave. And in fact, Wigner threshold law, we're all familiar with, tells you that cross-section should be temperature squared, and that's what they see. Very nicely. They got the exponent, I think, to 2 digits or something. Well, what does the Wigner threshold law say for three bodies? What should we expect to happen? Well, the Wigner threshold law depends on the long-range properties of the potentials, whatever interaction potentials there are. So, of course, we have to talk about hyperspherical now, okay? Because we're going to talk about Wigner threshold laws for three bodies. So somehow we have to create potential curves for three bodies. You've heard hyperradius a lot so far, so I'm just going to go through this pretty quickly. I wrote it down this way just to make it a little simpler to picture. Right? If we have three bodies, and these are going to be three identical ones now, the hyperradius can be defined simply as a sum of the squares of all the interparticle distances. So you really see that it's the size of the system. Now, Joe told us that adiabatic hyperspherical is a good way to do these things, which means that you take this three-body system, fix the hyperradius, and then diagonalize the rest. You somehow, for whatever reason, treat the rest of it as slowly varying. And Toru says that Fano says this was obvious, but every time somebody asks, I can't give them an obvious answer why they should be slowly varying. But nevertheless, it works out to be a really good approximation. And even better than that, it works out to be a good representation, right? Because you don't have to use it as an approximation. But when you do that, and it's obviously very similar to the Born-Oppenheimer, you get adiabatic potential curves for interacting three-body system. And this is what they look like. This is the total J equals 0, orbital angular momentum equals 0 potential curves for helium. So this is a boson system, but they look basically the same. So helium only has one recombination channel. It only has one channel that goes to a molecule asymptotically. So this lowest one correlates to the molecule of helium and then the free helium atom. And the rest of these correlate to the three free helium. So three-body recombination proceeds by coming in on one of these channels, undergoing some inelastic collision. There's some coupling between these channels, and they come out on the lowest channel. That's really what we're looking at. Okay, so now we've defined adiabatic channels. We can get back to our Wigner threshold law and figure out what it says for the three bodies. And to do that, and I'll just have the picture back up there again. To do that, you just need to know the asymptotic form of these incoming channels. They're the one that control the recombination rate. And you find that the three-body recombination rate simply scales like e to the lambda, okay, where lambda characterizes the long-range part of that. They're basically centrifugal potentials, right? Those continuum channels look like 1 over r squared with some coefficient up there. So they look like centrifugal potentials, okay? And so those centrifugal potentials are labeled by lambda, so naturally they come into the threshold law. It turns out when you have e to the lambda, that's a fairly strong dependence near threshold. So to compare with the experiment, it's important to do the thermal average, and John convinced me of that. And it turns out when you do the thermal average of e to the lambda, you just get threshold laws of t to the lambda, okay? Now the sticking point here is going to be figuring out what the heck is that lambda, okay? Because that lambda is going to depend on the particle identity, whether they're fermions or bosons, identical. It's going to depend on angular momentum, parity, and sort of all the other symmetry quantum numbers you can think of. So in the end, we can go through, and we've done this. You can go through and determine those lambdas that come in, and then figure out which ones are the dominant contributors to recombination near threshold. And here's a summary for all different combinations of identical particles. So let's go back to the maybe more familiar case. For three bosons, you expect that the recombination rate is constant at threshold. It's just like the two-body case. S-wave collisions dominate, and the cross-section goes to a constant at threshold. Well, that's the same thing here. Bosons, the recombination rate is a constant threshold, just like you expect. For even only two identical bosons and something else, recombination is still constant. But look when you get three. When you have three identical fermions, three spin polarized fermions, the threshold law is E squared, okay? And in fact, this is what you would have expected if you thought about it. You can only have p-wave collisions in a sense between all the different pairs. And so the rate is suppressed at threshold. It's not necessarily zero, right? It's not identically zero somehow. It's just simply suppressed. But it's also worth noting that the dominating partial wave that contributes here is 1 plus, meaning even parity, but total J equals 1. And we can just finish this table. If you have only two identical fermions, they collide in a 1 minus and are suppressed by a threshold law that's a factor of E. And then if they're all three different, well, there's no restrictions and it's constant at threshold again. Okay, so if we're going to look at three identical fermions, we want to look at this line. We're going to worry about threshold laws that are E squared, but we're going to look at the 1 plus symmetry to do the calculation. Of course, this threshold law only holds so long as there's no resonances in the way, right? Threshold law is going to be good unless there's a two-body resonance that lies close to threshold. When there's a two-body resonance close to threshold, you get potential curves that look like this, right? They aren't simply the repulsive centrifugal-like potentials I showed you before, in this case, these are actually potential curves for 3 interacting fermions, and there's a p-wave shape resonance, right? When you have a 2-body interaction and there's a p-wave, there's a centrifugal barrier, you can have a shape resonance behind that barrier. That's got to show up in the 3-body physics somehow. The way it shows up is as a series of avoided crossings above the threshold, okay? Now, Joe had a paper recently about Feshbach resonances in 3-body systems like that, and they see similar sorts of avoided crossings in that case, okay? But the point is, the threshold law is only going to be good up until for energies lying below that, where this curve still looks like that nice centrifugal long-range piece. When you get up here, it's going to break down, and who knows what's going to happen, okay? So to understand what happens near a resonance correctly, you're going to have to treat the physics around there. Well, okay, I'm going to follow John's lead here and say that's too tough for us right now, okay? Because that's actually a pretty tough problem. I can say more about that later. But what we're going to do is say, sort of to 0th order, what these resonances do is control the 2-body scattering length, okay? So the main effect that we're going to look at is what effect does that 2-body resonance have on the scattering length, or in this case, and I'll get to it in a minute, for p-waves we call it the scattering volume, okay? And we'll look at the recombination in that sense. Now, we all know that Feshbach resonances exist, have been used a lot. Here's one, for instance, from the Gilla group for potassium. And all I want to point out here is that you can tune the scattering parameter from -infinity to +infinity. It can take on any value. Okay, so in principle, anything's fair game. Using the scheme, though, that we only look at the effect of the tuned scattering length on the rate. We know that for bosons, that rate goes like the scattering length to the 4th power. Okay? So if we tune through a resonance, if that scattering length goes to infinity, well, our rate's going to go to infinity like a to the 4th. Okay? In fact, that's absolute value because that holds even when the scattering length goes to negative values. Okay? Near a Feshbach resonance, that doesn't look like it holds anymore. Joe's paper said that the power is a little different, but qualitatively the behavior is the same. It goes to infinity at the resonance and falls off around it. For fermions, we have to modify that behavior, okay? And just doing a little scaling, well, first we have to define what is our parameter. What's our low-energy 2-body scattering parameter? In this case, like I said, it's a scattering volume, and we're going to define it in analogy to the S-wave scattering length. And we leave it a volume just more for convenience. People have talked about it as a scattering length with a cube up here, but then you take the cube root of that thing and you get some weird behavior. In the end, like I said, the analogy with this boson a to the 4th scaling, for fermions, you get the scattering volume to the 8/3 power. So it depends a little more sensitively on the 2-body scattering physics. And again, as VP goes to infinity, as the scattering volume goes to infinity, we expect the rate to shoot up. So when you're tuning through a Feshbach resonance, you tune that rate through an infinity, you expect that it's going to get large, that the recombination is going to get large. And in fact, when we do the calculation, which means solving the radial equations, the coupled hyperradial equations on those potentials I showed before, just doing the scattering calculation, we can get the recombination rate for fermions as a function of the scattering volume, okay? And you see that it shoots up over here on the left side, and it, well, maybe doesn't shoot, but goes up pretty good on the right side, okay? And so, just sort of qualitatively, when you scan through a Feshbach resonance, you're going to be going from whatever the background value of this V is to large values of V. The rate's going to get higher, and then you're going to come back from negative values, and you should see the recombination rate even for fermions shoot up through a resonance. It's going to be greatly enhanced near a resonance, even though you're at ultracold temperatures. See? I should point out that what we're plotting here is K3 to the 3/8. Okay? Remember I told you that we expect the scaling to go like K3 to the 8/3. So basically this is just taking it out. So if our scaling ideas are right, then this should look like straight lines. This rate should look like a straight line somehow, right? That's why we plotted it this way. And in fact, down here for small values of V, the black line up there looks like it's pretty straight. The red line doesn't. Now what's the difference between the two? The black line is the actual rate, is a function of energy. Okay? The red curve is the thermal average. Okay? And again, that thermal, we're treating energy, we're kind of using it a little loosely here, right? This is all calculated at an energy equivalent to 5 microkelvin, right? But then you do the thermal average also at 5 microkelvin. Okay? And the thermal average then, of course, brings in all energies. Okay? But the black curve shows the scaling we see, the straight lines. It shows the straight lines pretty well. And then the red curve doesn't show it quite so well. But can we understand the features of this curve? I mean, is there some physics to extract here? Okay? Well, maybe to appreciate that and just sort of get a better feel, let's compare it with what happens for bosons. So if you plot the recombination rate as a function of the scattering length for bosons, same curve we just saw basically, except for we're taking the 1/4 power, okay, to take out that behavior. So straight lines here show the scaling behavior we expect for bosons. And in fact, we see a little more, some more interesting features here maybe than we did for the fermions, in the sense that over here on the plus side for A, there's a minimum in the rate. The rate actually goes to a 0, okay, or at least a minimum. We see over here on the negative side that there's a resonance, an enhanced recombination rate, and that comes from a 3-body shape resonance. Now, how do I know those things? Well, we go back to the adiabatic hyperspherical potential curves, and we use those to interpret this picture. Okay. Now, the dotted or the dashed lines show the straight line scaling behavior we expect, and here it actually holds pretty well. But what about that fermion picture? Can we understand it? Right? We don't have any minima. We don't have any obvious spikes in here. We just have different behavior on the plus and minus side. But are those things understandable? Well, I said for the bosons, we understand it from the hyperspherical potential curves. So let's look at the potential curves for the fermion case. Okay? Again, this is potential energy as a function of hyperradius for a positive value of the scattering volume. So we're over here on the right side. Right? Remember what the picture was over here on the right side. Okay, we're over here, 10 to the 6, I think that's right there, 10,000 on that plot. And if you look at several of these things, which not so easy to show here, if you look at several of these things, you can see trends. How do these potentials behave as you change the scattering volume? Well, there's actually, in this lowest channel, for instance, there's a centrifugal barrier, right? This thing goes out to a P wave, so there's got to be a centrifugal barrier. The upper channel, as you make the scattering length or the scattering volume more positive, larger and positive, this entrance channel, the continuum one, gets more and more repulsive. Okay? So at a fixed energy, as you increase the scattering volume, the turning point gets further and further out. Okay? Seems like probably you should expect the rate to go down. If the turning point's further and further out, you aren't going to penetrate to the interaction region. Well, it happens that the coupling also goes to larger distances as VP grows, as the scattering volume grows. Okay? Although it does it a little strangely. The red curve here shows the coupling between the two curves. Okay? So the peak in the coupling stays at the same place as a function of the scattering volume. The shoulder, however, stretches out to a really large distance, and that shoulder just keeps stretching out as you increase the scattering volume. Okay? Now, just like for the boson case, there's a barrier in this entrance channel. Maybe you can get tunneling resonances and get peaks in the recombination. We haven't seen that yet. That doesn't mean they aren't there. And since there isn't any other work really to compare with, the limit as VP goes to infinity, we really don't know quite what to expect yet. I think there's some interesting physics there, but that really is going to have to be pulled out with some analytic treatment. I think the numerical part becomes problematic going to that limit. Okay? So the trade-off between the turning point in that interchannel going further out and the coupling going further out, well, to be honest, it's not really clear which wins yet. We're still trying to look at that. Now, for the negative case, when the scattering volume is negative, you have a barrier in the entrance channel already. That's just like the boson case. Okay? You have a barrier in the entrance channel, so the incoming wave is going to come in, scatter off that barrier, and in principle can tunnel through to where this coupling is large, the red curve, and recombine. Okay? What happens to that barrier is you change the scattering volume. It moves to larger and larger hyperradius also. As it does so, the height of it shrinks. So it's at some point for a fixed energy. Now remember, we're looking at all this at ultracold temperatures, so we fix the energy and we're changing the potential. So at some point at a fixed energy, that barrier is going to come below the energy, and you can go right over the barrier into this region where the coupling is large. Okay? And recombination should be greatly enhanced there. And that much is clear from the picture. In fact, we don't go out far enough yet. I think it's about minus 20,000 over here, that at this scattering energy, that barrier would actually come below. And at that point, the recombination rate reaches essentially the unitarity limit, the unitarity limit imposed for this channel. Okay? Again, tunneling resonances are possible. We haven't seen them yet. This is still work in progress. So we can fill in some of the physics on this picture like we did for bosons. We don't know what's happening in the limit of large VP. Right? I'd like to see some work there. I think interesting physics is possible out there. Maybe there's tunneling resonances because there's barriers in the adiabatic potentials in both cases. Then over here, we know when we go to large negative values, that barrier and interest channel comes below your energy. You get greatly enhanced recombination, so you reach the unitarity limit there. In fact, I think we've only actually seen it come within about a factor of 3 of that unitarity limit, but it's pretty close. But we still haven't said what in this picture do we see any effect of the two-body shape resonance, and is there a possibility for this minimum that we saw for the bosons? Well, again, things that we're looking at, okay, but haven't really settled yet. There's some evidence, you can't see it here, but there's actually a little bitty tiny peak down there that looks like it's an interference, actually maximum in this case. It looks like there might be an interference minimum if we go further out, but that's not obvious yet either. So the work near the resonance is we really need to push a little bit. I have those pictures. The problem is that as you come in on this entrance channel, there's an infinite number of these crossings. As you come in from infinity, right? Imagine a little wave packet starting out here. Little pieces of it can shear off and go up there. Well, what does it mean when there's a little piece up there? That means essentially what you're doing is you have a molecule in a resonance being hit by the third atom. Okay? You might think that plays a role in recombination, right? If you whack something in a resonance, surely it's easier to drive it down into a bound state and really get recombination. The problem is, right at that energy, it's really hard to do the calculations, just a practical matter. Lots of partial waves start coming in, and really we just haven't nailed it all down yet. Now, we asked before also, what are the effects of it being in a degenerate Fermi gas? Well, there's possible statistics issues that I really don't have any idea for. But what about polyblocking? Okay, that we've thought about a little bit. And the issue is if the two-body binding energy, the binding energy of the molecule you make, is less than the Fermi energy, then that free atom has nowhere to go, right? You make a molecule and a free atom. The free atom has nowhere to go if it can't get above the Fermi energy. Okay? Well, when is that going to happen? At a fixed, well, assuming basically zero collision energy, you can make an estimate. The bound state basically for the molecule is h bar squared over 2 times the reduced mass of the molecule times Vp to the 2/3. Okay? That's where you get the 3 halves. So that means that for potassium-40 with a Fermi energy of like 360 nanokelvin, Vp actually has to be near 10 to the 10th. Okay? I only showed out to about 10 to the 6th or 7th on my picture, so we can't get out that far. So maybe we have to appeal to experiment. And we actually, fortunately, have an experiment to appeal to. The black dots are recently measured experimental values from Debbie Jin's group. And what they've done is they've tuned through a Feshbach resonance for a gas of pure 9 halves minus 7 halves potassium atoms. Okay? And they measured the 3-body loss, and they see a peak. Okay? Well, the lines are our calculations taken from the picture I showed you before. Okay? We had to convert. We had the recombination rate as a function of scattering volume. So there's a conversion here to get it as a function of magnetic field. So we had to use John's 2-body data to take it from the scattering volume to magnetic field, and that's how we get this series of curves. Okay? What I've shown is basically different temperatures. These are thermally average rates. So for 2, 3, and 5 microkelvin, the rates slowly, or the widths of these things slowly increases. The experiment energies were typically between 2 and 3 microkelvin. Okay? I also show this green curve, which is at 3 microkelvin, and basically just uses a different parameter in our model 2-body interaction. I really didn't say much about that, but the point is there's a little bit of freedom in the theoretical model we're using, that there's one parameter left over that we can use basically for fitting. It doesn't look like it's helping us a lot. We can match the top rate, but we still can't match the shape. With different parameter, that's what the R0 is the parameter. With a different parameter, we can match the position and closer to the shape, but we can't match the magnitude. But there's no evidence here for any of that polyblocking issue, because the values of the VP that I was talking about would basically be right there and so close to the resonance that there's no way they'll probably ever see it. Okay. So to summarize, we've done calculations for recombination, which are essentially exact given the interactions we're using. Looked at the general features of fermion recombination, tried to identify the physics, the physical mechanisms that are behind them. We're still obviously working on that. And able to show some qualitative agreement with the experiment. The shape of those curves looked awfully close. It had the asymmetry just that the experimental had. And as I mentioned, lots of unanswered questions, but hopefully lots of interesting physics to find there. Thanks.